Okay, so hopefully this pendulum is familiar to you from the laboratory exercise that you did earlier in the semester. At that point in time, we didn't derive the equation for the period of the pendulum. We're going to do that in this lecture. Now, this type of pendulum is known as a simple pendulum, and that's because there's this string here that we can model as massless. And at the end of the string, we've got a bob, and we can model all the mass of this bob as being at the center of mass. So you saw in mechanics why you could do that. Okay, so let's just look at how this pendulum swings for a minute. Okay, so what we're going to be showing is that this motion is simple harmonic, but just for a minute, let's stop the bob there and let's consider the forces acting on it. If I wasn't holding this, there would just be the two forces acting on it. We've got the tension acting upwards along the string here, and then we've got the weight force acting downwards. So we'll be looking at those now to show that this is undergoing simple harmonic motion. Let's consider all the forces acting on the pendulum. We've got the tension force acting upwards and the weight force acting downwards. So let's just draw them together as a vector diagram. Here's our tension force, here's our weight force acting downwards, and the angle between the tension force and the weight force is theta. So the angle between the tension and the resultant force is 90 degrees, as the resultant force is directed along the arc of the circle, and as the tension is the radius of the circle, they meet each other at 90 degrees. So we can see that the resultant force is equal to mg sine theta just from simple trigonometry. So we've got the resultant force is equal to mass times the acceleration. The negative here is because it's a restoring force, it's trying to move it back towards the center, and our acceleration in this case is d squared s dt squared. S we're taking as our position coordinate, it's the position along the arc of the circle, and arc length is equal to s is equal to L theta, and so this is the s in here. So we can actually replace this s with a theta. L is not changing with time, so when we take the second derivative with time, L just remains a constant up the front. So we have d squared theta dt squared is equal to minus gl sine theta. That's replacing d squared s dt squared with d squared theta dt squared times L, and then rearranging it. Now we can, assuming that theta is small, when theta is small, sine theta is approximately theta. So we can write the equation in this format. So we've got d squared theta dt squared, i.e. the acceleration of theta, the angular acceleration, is equal to minus g on L theta. Now this has the same format as our equation for simple harmonic motion. We've got the angular acceleration instead of the acceleration, and the angle instead of the position. So we can equate omega squared and g on L. When we do that, omega is equal to the square root of g on L, and then we know the relationship between period and omega. Omega is equal to 2 pi over the period, and so t is equal to 2 pi root L on g. Now you've used this equation in the pendulum laboratory exercise to work out little g. Now simple pendulums aren't the only type of pendulum. Any shape can oscillate about some pivot point, such as this one. Objects such as this are known as physical pendulums, and we'll be deriving an equation in a minute to show the period that these physical pendulums oscillate at. You'll see that it's proportional to the distance from the center of mass. So let's just find the center of mass of this object now. To find the center of mass, we can hang it up. And then if we draw a line directly downwards, this shows one axis along which the center of mass can be found. And then we can hang it from another angle, another side, sorry, and when we draw a line directly downwards, this shows another axis along which the center of mass can be found. So where those lines cross is the center of mass here.
And the distance from the pivot point to that centre of mass we'll call d in our equations. So then when we oscillate it like this, we'll show that it's undergoing simple harmonic motion, and we'll now derive the period of that simple harmonic motion.
Okay, now you know from rotation that torque is given by r cross F, where r is the vector pointing from the pivot point to the place where the force is applied, and F is the force vector. So r in this case has magnitude d, F has magnitude mg, and so this becomes dmg sine theta. This is actually directed into the board in this case. And so Newton's second law for torques tells us that the sum of all the external torques is equal to the moment of inertia times the angular acceleration. So substituting in here, we need the negative sign because this is a restoring force. It's working to get this pendulum back to its equilibrium position. We have minus dmg sine theta, that's the entire torque acting on this, is equal to I, and alpha is just the angular acceleration, which by definition is d squared theta dt squared. So we have d squared theta dt squared is equal to minus dmg theta on I. We're making the small angular approximation here and replacing sine theta with theta, and equating this to simple harmonic motion. This is equal to minus omega squared theta, telling us that omega is equal to the square root of dmg on I, and so the period is given by 2 pi root I over dmg, where d is the distance between the pivot point and the centre of mass, m is the mass of the object, and little g is just the acceleration due to gravity, and I is the moment of inertia of the object.